Hello everyone, it is August 16th and this is the bi-weekly libhal meeting. Alright, for the agenda today, we're going to go over low power functions for ARM Cortex and processors from nano newlib to pico libc, and then also look at libhal macromod, which is now in the alpha stage. Low power functions for ARM Cortex. So there are a couple of new APIs that have been added. They are the wait for interrupt and wait for event APIs. Underneath, they just simply execute the WFI, which stands for wait for interrupt instruction, and the WFE, which is the wait for event instruction. Now, if you were to take a macromod or an STM chip or whatever you're using and run these functions on them, as long as it's a ARM Cortex M processor, you will see a reduction in power usage. The idea is that it'll basically stop the CPU and reduce power consumption, waiting for some other event to occur. In this case, it depends on the situation, but you might have like an interrupt occur whenever serial comes in, or for USB, or for CAN, or for something. Basically, you can stop the device and then wait for some external interrupt to cause you to wake back up. Depending on the MCU, additional power savings can be achieved. This is just the start. I'm still getting more knowledgeable about ARM Cortex and its power states. So this is still very new for me. I have used these instructions before, but yeah, not to. I haven't gone that deep. Really, it was call this function, and then the rest happens. So yes, that's what we have now, which can be implemented in projects right now. But for now, I think it makes sense just to, if your project does not need it, not to worry about it as much. Now, the next big thing for libhal is going from nano newlib to pico libc. So first, what is pico libc? Pico libc is a library offering standard C library APIs that target small embedded systems with limited RAM. Pico libc was formed by blending code from newlib and AVR libc. Now, because AVR systems are 8-bit, they're very, very limited in processing power and in memory footprint. Usually devices are also like very small in terms of flash and RAM, so that's a really good pick for something that's really limited. Now, why use it over newlib or newlib nano? Now, we've been using newlib nano at the moment. They also have their own C library implementations. Newlib is mostly for OSs, so if you actually use it, your binary usually jumps, how much was it? Like up to like 50 kilobytes and maybe even like 100 kilobytes. Just a whole bunch of different things being thrown into your binary that you're probably not going to use. I think even, not locales, but I believe some other nonsense gets thrown into your binary if you use newlib. Newlib nano targets embedded systems. And you can kind of see the wordplay here with Pico and Nano. Pico is like an evolution of the libhal Nano project. Now, previously we were using libhal Nano, but there were several problems. But the main ones here have to do with code bloat and limited startup code. One of Pico libc's improvements is code size. If you look at the blinker example for the macromod for the LPC 4078, with just normal newlib Nano and quite a few of the APIs, newlib nano with no sys, which basically means like it's a setting you can turn on or a specification you can turn on for not implementing any of the typical operating system like APIs, like accessing files and that kind of thing. With all that, the binary size was around 21 kilobytes, 21.5 kilobytes. With newlib nano plus pico libc, it goes all the way down to 6,200 bytes. That's a 71% reduction in code size. That is huge. And the funny thing is that it actually provides us more than what newlib nano provided us. But along with all these savings, we also get a savings for the BSS section, which is the uninitialized data inside the application. So about 25% reduction in BSS and a 71% reduction in code size. Now, I use Blinker as an example because blinkers should obviously and honestly be very minimal. There shouldn't be much happening in them. Now, in our code, we do set up the PLLs and maximize the CPU speed. So that goes into the binary size. But yeah, it's a simple example. We got down to 6K. Could we go down lower? I am certain of it. Actually, I think I've done such a thing in the past, but it's not. It's more of an exercise, in my opinion, than it is of any real utility. So now, how's this possible? Well, the creator of picolibc adopted tinyprintf and other size optimal implementations for its C libraries, greatly reducing its code size. There are a lot of times when a lot of C libraries will try to optimize for speed, and because of that, they will have a whole bunch of branch conditions, and they will handle certain situations differently. I believe I saw recently that there was an update to, I think it was ATAN 2, where the guy who made this is called Keith. He basically noticed that, or maybe someone else who contributed, noticed that there was an edge case that ATAN would normally go through and run through. Now, that edge case required more code, but if you get rid of the edge case, it can still work. It just has to do more, has to perform a little harder, has to run a couple more loops. So I was like, okay, that's a really cool way to kind of think about code size over performance. So that's the design of picolibc in terms of code size. It greatly reduced our code sizes, making flashing a lot faster. So this is going to benefit us in a lot of different ways. The next benefit that picolibc has is limited startup code, or at least, sorry, not limited, but actually non-limited startup code. Nulib's Nano's CRT0, which is, I forgot what the terminology stands for, but the startup routine, normally named as CRT0, does the following. Sets the stack register to the top of stack, clears the BSS section, and runs global initializers and constructors. But what it does not do is copy the data section, which is all the initialized variables, from ROM to RAM. It also does not turn on coprocessors like FPU. Now, here's the interesting thing. I can kind of understand why the .data section was not included. It makes sense because if you think about what nulib was normally run on, it's normally run on a operating system. And in general, the way that binaries are organized, it depends on how you want to place things, but usually it's your code and then you have your data at the end, and then you have some marker to indicate how big the BSS section is. When you want to load or run a program, you have to load it into RAM. When you load it into RAM, the instructions are already in RAM, and then the data is already in the place it needs to be in RAM as well, specifically if you do position independent addressing for your application, which is almost always the case you're going to do. So with that, this means that your BSS section can just allocate some memory ahead and then fill that out with zeros. On an embedded systems, you a lot of times execute directly from flash. There is no moving data from flash into RAM. So if you want to actually reposition your data section, which is currently in flash, if you tried to write to it, it would crash. Reading from it would work, but you'd never be able to update it. So to get it updated, you have inside your linker script that the data section from one section goes into RAM later on, and you address it from there. You make the copy into RAM, and then you're good to go. So I believe because of this thought of, well, we're going to make it the same as you would on an operating system, they did not add in the extra code to copy from ROM to RAM. This picolibc does do this, though. Another one that I find very peculiar is that it doesn't turn on the coprocessors or the FPU. It might be because it thinks that doing so is a choice that the user must make in order to ensure that their program or their application consumes more or less power, depending on what they want to choose. I think the one thing about this, though, is that I guess a part of me is a little biased, maybe allow them to turn it off rather than not having turned on, particularly because if any instruction inside your code ever accesses an FPU register, just for storage, not even for like doing any calculations, it will crash your system because the FPU is turned off. It'll attempt to talk to it. It won't get anything back. It'll think that there's something invalid with the state of the entire program, which there is, and then it'll reboot you or hit a hard fault and then get stuck. So having this default turned on, especially when you have an FPU, makes sense because it's most likely that you're going to utilize it in the instructions of your code. picolibc does all of this and also has a way to configure TLS, thread local storage, as well at startup. We'll probably go over that later when, well, if and when I or someone else adds native TLS support into libhal for RTOS. What this will kind of end up doing though is if we make that happen, it's likely that we will have to bind ourselves to picolibc, which I think is not a problem. Picolibc is really taking off, getting updates all the time. It is way more active than newlib, and it also has support for RISC-V and Extensa, and I think also AVR and everything else. So basically, it is a fantastic library for all of our embedded needs. So yeah, that's picolibc. Next up, we have libhal macromod in alpha stage. I'm gonna do a bit of a live demo. Before I go there, I want to answer some of the questions that I asked before. I came to some conclusions, and if anyone has any particular thoughts or feelings about it, you can ask in the discussions or in the comments. But basically, I asked the question before, which is, what clock rate do you use for your microcontroller? Now, like I said before, we could have done like a ratio from like 0 to 1, and then that be a ratio that you then multiply against what your maximum speed could be. But that's complicated because if you have one device that can be 1 megahertz and one device that can be 100 megahertz, and you want to set your baud rate to 1 megahertz, the 1 megahertz device is not going to have enough clocks in order to actually fully run UART. Or even worse, if it's less than 1 megahertz, then you literally can never achieve that speed. So what do? Well, the other option is to just simply bump this thing up to the absolute maximum and run at maximum speed at the highest clock rate that is standard. Now, or supplied. I say that just because the STM32F103, although I believe it says it can only go up to 72 megahertz, you can actually bump it up to 120, and it seems to be rather stable at that level too. Maybe at some devices, won't work, but all the ones I've tried with work just fine. Anywho, we want to set it to a maximum. One is because we can know what the maximum is. There's only one number that is the maximum, and it can be calculated with the one other number that you need, which is whatever your clock frequency is, whether that's from an internal clock or from an external clock. The micromod has that well defined because it knows the exact components that are used for itself. So we can hard code that directly in. And then also we know what the chip's maximum speed is, so we can hard code that in directly as well. So that makes choosing what the initialization sequence should do pretty obvious and easy. But now we think to ourselves, okay, well, how do we handle power savings? Well, we can do a technique called race to sleep. Race to sleep is a technique where you bring your clock rate up as high as you possibly can, and then what you want to do is you want to do as much CPU or RAM or whatever bound operations as you possibly can do, and then once you hit the end, you then immediately try to go to sleep. Now, if you're running with an RTOS, that means every 1 millisecond, or let's say every 1, 2, 5, or 10 milliseconds, you may go to sleep. The rest of that time, you spend pretty much either waiting for an interrupt to occur to knock you out of sleep so you can do some real work, or you spend most of it sleeping. And what's going to happen is, let's say the FreeRTOS tick goes, you're going to going back into a thread, do some work, and then come back into idle, or there's nothing to do, so you stay in idle. If you just stay in idle, then you wake up a little bit, check to see if there's any work to be done. You don't see there's any work to be done, go right back to sleep. That ends up saving you quite a bit of power relative to simply just reducing down the clock speed, which would make you slower, which means you spend less time actually being in sleep. There are situations that I've heard from coworkers where that's not the case, where actually reducing the frequency was better for them. But I think we can look at the majority case and say that race to sleep is probably going to be a good choice, and it makes our lives easier. Next up, we have, should console be implemented as a serial port? And yes, 100%. Basically, even if the underlying technology is I2C or SPI or USB or whatever, it can always be related back to, you have some serial buffer for receive, you have some transmit buffer that you want to send. And that's about it. So that's the Micromod solutions. And then from there, I'm going to show you guys just a little bit of what Micromod's APIs look like and a couple of new documentation for this. So let's go to Micromod. I'm going to zoom in on this. Okay. The ones that are interesting are basically like the core. After that, they're all pretty obvious. But we have initialize platform. This is initialize the system. Should be the first thing called at the start of main. Typically sets up data section, heap sections, BSS, applicable, interrupt service routine handlers. That might be necessary. Anything else that might be needed in order to run the MCU. So this is where all that stuff happens. Um, yeah, that's pretty much it. These are actually pretty minimal for LPC, and actually most things are going to be in ARM because Pico libc eliminates the need to do a lot of this extra stuff, like the data and BSS section setup, as well as the heap section setup. That's all handled for you. But still useful to have this API so that anyone who's writing an application can just run it immediately, and if they use some other bespoke device that does not follow what we're using, it'll still work. Cited clock just gives you back a way to measure how long the processor has been up. Side note, the DWT timer I actually need to update to incorporate sleep cycles because currently it only supports the awake cycles, which means that if you do sleep, you will lose those other cycles and your idea of time will be off. Then we also have a system timer. This is mostly used for setting up an RTOS. Obviously, other particular interrupts may need to be enabled as well, but at least you have some way to generate a timer so you can run an operation over time. Here we have our inter power savings mode. This is still like in a beta testing type phase. I'm still thinking about how this could be done better, thinking if there should be a deep sleep or a turn off or power down type operation. We obviously have a reset function somewhere here. Yep, reset. So maybe that will make sense, like a power down operation. But at the moment, I'm not exactly too sure. Then here we also have console. So like I said, console will just be a serial port. You have to give it some type of receive buffer that it can use to hold any data received over whatever port it's using. And that's about it. The rest is pretty self-explanatory, but I'm going to make one little change here. I've been thinking about this for a while. If this output pin is set to true, the LED must be on. If the output pin level is called with false, the LED must be off. Now the reason why, so basically I was thinking about this yesterday. My LED function has an output pin. Now that output pin could either be open drain or open source. And we don't know which one it might be set up to. We don't know if it's going to be supplying the current to the LED. We don't know if it's going to be just be the connection to ground for the LED. That's not really too knowable, and it could switch up no matter what. So what the software has to do is know how the chip is set up and then invert the signals. So we don't have a output pin or a pin inverter yet, but if someone wants to write that soft driver, that'd be great. That way you could just easily if you know it's inverted from this logic, you could just pass it into one of those and then pass that back out. The rest here is pretty obvious. You just have all the different names for like the driver for ADC pin 0, driver for ADC 1, driver for the battery pin, DACs, PWMs, everything else. Yeah. And that should... Oh, yeah, and then we also flatten the namespace. So now it's output underscore G, input underscore G, interrupt G. Now, if you do try to use interrupt G and then try to use input G, the behavior we are going to say is undefined, but what's most likely to happen is that the input G will take over control over that pin, and then the interrupt pin that you generated will no longer work as expected. Actually, trying to call the interrupt pin later on will definitely be undefined behavior and could definitely crash your system or do something worse. The input pin would probably be valid, but that is also not completely defined. It really depends on how the drivers are implemented. This has made me think a bit about if there should be some way to determine if drivers conflict with each other. And this made me think, could you do this in C++? And I'm certain you can. I'm very, very certain you can. I did something somewhat, well, it's really difficult if you do it in C++, and I could only imagine that it would be extremely time-consuming for the compiler. Yeah, all types would have to know about each other and would have to be able to like know that you somehow used each other. Actually, maybe that's not even possible in separate compilation units. It all have to be one big compilation unit for it to be able to kind of know that. That's all to say that I thought to myself, what else could be done to figure this out? And I realized maybe there's some idea, and this is just far-fetched idea of the future. Not planning on doing this anytime soon. But a lot of people think about how to make the code know whether or not something is messed up. But what if we just made the binary know that, put information into the binary, and then use that to figure out things are messed up? So if you try to grab interrupt G0, if we can somehow do that statically so that we could create a unique value saying, hey, G0, or let's say the underlying pin is like 1, 5 or 0, 5 on the LPC. Well, if it's port 0, pin 5, and we can put that somewhere in the binary, and then we can put it through some post-processing to say, hey, this particular pin is associated with, this particular pin number is associated with this object somewhere in the binary, and then find another one for an input pin that's also 0, 5, and see that's associated somewhere in the binary. At the very least, we could at least warn the user saying, hey, this particular pin is used in two separate locations as two separate objects that conflict with each other. Is that what you meant to do? And yeah. But now the interesting thing is that could you take it even further? Do some more binary analysis to see if one dies before the other one comes into existence. So you could at least say, hey, you're using them in separate places. They do conflict, but they don't conflict over the same time. And effectively, as I thought about this more and more and more, I realized that maybe that could be a way to create a borrow checker or some sort of C++ checking mechanism as a post-processing step. Because then C++ could live as it is without having the horrors of having a borrow checker injected. Not saying there's anything wrong with a borrow checker, simply saying that introducing it into the language would basically break everyone's code, and nothing would work, and then C++ would die, effectively. Or at least it wouldn't grow any way towards beyond that point. But if you have it as an opt-in thing afterwards, I can see a lot of people using that as part of the CI step. So that was an idea, just something that I thought about. So yeah, let's look over here. We can look at some of the code here. We can go over to demos. Everything should look about the same as we saw before. We have initialized platform, application, reset, all that goodness. And then in Blinker, we have all of this. There's also two additional applications. I don't believe we had the console loopback application, which just echoes back whatever you send it. And then also same thing with Hello World, just simply sends out Hello World every half a second. And if I go over here and I try to build this, build LPC, let's change that to build. Oops, daisy. Cool, so we got our Micromod demos done. We can build for all of them. I don't even remember if I went over this new feature, actually. Actually, I don't think I did. All right, so there's something interesting about Micromod demos. So let's actually look at the code sizes real quick before we move on. So here we can see that the console loopback is only 6.1K. And if we look over at, let's see, what is this one? Blinker, it's about 6.3K. I'm surprised that one's actually, why is this one bigger? It's only blinking. Oh, sometimes it doesn't use a timer. That's why. Oh, it does actually use uptime counter. Oh, that definitely gets optimized away. That's not even used. I should clean that up. Yeah. But yeah, no. Yeah, so not only, so one is the binaries are small. So that's great. That comes from picolibc. But also we have this little section here, Micromod demos, that shows you how many of them got built. Because check this out. We actually don't have a UART driver yet for STM32F103. So there's no way that this is going to work because it shouldn't. It's not going to link. So when we go to run this, we'll see that some of these failed and some of these worked. So the idea of Micromod is actually that we iterate through all the possible demos. We iterate through all the possible demos, and we only use the ones that really work. And that's just going to be a thing that's going to happen. Like we said before, if you don't have a certain pin or a certain peripheral needed for a particular application, it should fail on you. Just simply not link, so you don't have to go through the process of flashing it and seeing if something actually works. It should just tell you that this is not going to be compatible. And that's what these demos do. They show you which ones break here that just aren't going to be available for your use case. These will eventually work once we bring in UART, but we don't have a audio port for the STM, meaning that if there was an application that used a future audio interface, we could not actually build an application that does that for this one. So yeah, that's pretty much the tour of Micromod. Yeah, the hope is that more applications could just be built using the Micromod APIs, and then you just don't have to worry about, well, where the underlying implementation comes from. You just write your code as you would want to and use whatever resources are available, and the rest just comes for free. And that's pretty much it.